Hi, class. Here's another lesson via video. Um, we're going to talk about lesson 5.7. Excuse me. And let me know what questions that you have. So I first of all need to share my screen. I don't know why it spins sometimes. Here we go. Still spinning. There we go. Okay, so we're going to look at some more integrals and the idea of what we call a differential equation. Starting with a little joke here. Um, since we're taking the derivative with respect to n, everything else is just a constant. And I would put that constant times n, and don't forget the plus c. Get it? Yeah, nothing's funnier than math humor. All right. So, again, integrating is basically just going backwards from taking a derivative. So we're going to look at some derivatives that we've done and use that to lead us to some integrals. Excuse me. Um, so the derivative of e to the x is e to the x. So the integral of e to the x would be e to the x. Don't forget that plus c. Okay, so that one's pretty simple. Um, the derivative of a to the x is a to the x natural log of a. So if I'm going to take the integral of a to the x, I'm going to have to put a 1 over natural log of a in front plus c, so that when I take the derivative of this, it'd be 1 over natural log of a times natural log of a, and they would cancel and give me just the a to the x. All right. The integral of arctangent is 1 over 1 plus x squared. So the derivative, did I say integral? The derivative of arctangent is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared will just be the arctangent of x. And looking here, the derivative of arcsine is 1 over the square root of 1 minus x squared. So if I have the integral of 1 over the square root of 1 minus x squared, that would be equal to the arcsine of x. And the derivative of natural log is 1 over x. So the integral of 1 over x, it seems like it should just be natural log of x, but there's a little bit of a twist here, which is that I need to put absolute value signs around the x. You have to take natural log, you have to be plugging in a positive value into that. So we're going to put absolute values around the x to make sure I'm plugging a positive into natural log. So note, absolute value sign, absolute value signs. All right. Okay. So let's practice using these. Integral of e to the x, well, that would just be e to the x. The integral of x to the e, so that's the same as like x squared or x to the fifth. I'm using the power rule, it's just that the exponent is e. So I will add 1 to the exponent. Okay, I didn't write that right. X to the e plus 1, and then remember I have to divide by that new exponent. Plus c, always plus c. 5 over 1 plus x squared. Okay, so that's the same thing as 5 times 1 over 1 plus x squared dx. And 1 over 1 plus x squared, that's my arctan of x, plus c. Remember, whenever you have a constant times a function, that constant can get pulled in front of the integral. So when you have a constant times a function, you're taking the derivative, you just do a constant times the derivative of that function. Okay, 4 to the x now, 4 to the x dx is going to be 1 over natural log of 4 times 4 to the x plus c. Okay, so that's just a direct application of this rule up here. Okay, 5 over 4 square root 1 minus x squared. Okay, so I can bring that 5/4 out in front. And that's the integral of 1 over square root 1 minus x squared, which is arcsine of x. And don't forget your plus c. Okay, 3 over x, so that's 3 integral 1 over x dx. 1 over x, that's natural log of absolute value of x plus c. Sometimes people get a little bit confused and they think, oh, hey, let's just rewrite it as 3x to the negative 1 and then use the power rule. But here's what happens if you try that. You have 3x negative 1 plus 1 is 0, and then you're multiplying by 1 over that new exponent. But hey, can we divide by 0, folks? No, we cannot. So if you try to integrate it using the power rule, you'll run into a problem, which will hopefully lead you to go like, oh yeah, this is the one that's natural log. I don't use the power rule. All right, here, I can use the power rule, okay? It's only when I have just x in the denominator that I'm going to do the natural log of thing. So I add 1 to the exponent and then multiply by the reciprocal of that exponent. So that'd just be a negative. Okay. All right. 5x plus 3 over x. As we've talked about, you've got to separate into the two fractions so that you can use power rule. That would just be 5 plus 3 over x dx. So that's 5x. I lied a little bit. We're not using power rule on 3 over x. We know that that is equal to the natural log of absolute value of x. So it's 3 times the natural log of the absolute value of x plus c. Here, e to the 2x over e to the x. You need to get it down to one term if you can, because you can't just take the derivative, the integral of each of your numerator and denominator separately. Remember, we have that fancy quotient rule for derivatives, so we can't just go backwards with quotients. Well, that's just e to the x, and the integral of e to the x is e to the x plus c. So that's kind of cool how that turned out. All right, moving on to page 3 of our notes. More examples here. Evaluate the following definite integrals. So x minus 1 quantity squared over x squared. I'm going to have to use FOIL to expand that numerator. And this is still from 1 to 2. Okay, so now I'm going to separate that. X squared over x squared minus 2x over x squared plus 1 over x squared dx. Okay, let's simplify that a bit. I have 1 minus 2 over x. 1 over x squared, I'm going to write that as x to the negative 2 because it's a little bit easier to take the derivative when it's written as a power. I did not rewrite the 2 over the x because that's the natural log guy. All right, so integral of 1 is x minus 2 natural log absolute value of x. X to the negative 2, I add 1 to the exponent, and I'm multiplied by the reciprocal of negative 1. and I'm evaluating from 1 to 2, right? That's our fundamental theorem of calculus. Obviously an important one anytime it's called fundamental theorem, that's a biggie. All right, so I plug in the 2 minus natural log of 2. I can drop the absolute value because the absolute value of 2 is 2. Minus 2 to the negative 1. Okay, that's plugging in the 2, plugging in the 1. 1 minus 2 natural log of 1 minus 1 to the negative 1 would be 1. Now, I hope you know that natural log of 1 is, yes, hope you're all thinking it, it's 0. So I have 2 minus, and hey, just to make sure we remember our log rules, 2 natural log of 2 is natural log of 2 squared or natural log of 4. I prefer writing 1/2 here. Minus, okay, so the 1 minus 1, those go away. Natural log of 1 is 0. So that whole thing, that whole term is 0. 2 minus 1/2 would be the 3/2 minus natural log of 4. So that would be my final answer on that one. That's some fun math. All right, so how do I do an integral of an absolute value? Well, remember, there's not really a rule for taking the derivative of an absolute value. We had to break it up into a piecewise defined function in order to do the derivative. And so we would have to do the same thing in order to do the integral of an absolute value function. The easiest thing to do with this one, though, rather than really try and rewrite it as a piecewise defined function, is to graph it and do the geometric, use our geometric rules. So 2x minus 1, absolute value of 2x minus 1, I know it's going to be a v. If I set 2x minus 1 equal to 0, I get x equals 1/2. That's where the vertex of my v is. Okay, and I'm going from 0 to 2. So it's this area and that area. Plugging 0 into the function, I get 1 after I take the absolute value. So that height is 1. I need to know this distance as well. So I plug 2 again into this function here. 2 times 2 is 4. 4 minus 1 is 3. That height would be 3. So the integral from 0 to 2 would just be 1/2 times the height times the base for this first triangle. For the second triangle, it's 1/2 times times the height times the base. From 1/2 to 2 would be 3/2. And then I just need to do a little arithmetic. So I would have 1/4 plus 9/4, which is 10/4, which is 5/2 would be my answer. So sometimes it is easiest to go back when we have the absolute value. It's easiest to go back and use the area underneath the curve and use geometric formulas. All right. What the heck? Changing topics just a tad. Going to talk about what a differential equation is. It's an equation which contains a derivative, and what we're looking for as a solution is the function. Now, these can be really crazy, like y double prime minus 2y prime plus 3y equals 5x minus 2. Okay. If that is an example of a differential equation, you can have first and second derivatives. You can have however high a derivative as you want. The goal again is to look for the function y that satisfies this equation. This is beyond what we can, something that we're going to be able to solve But I just wanted to show you what that might look like. Um, so we're going to do really, really simple differential equations right now. We will do differential equations that are just a little bit harder than this. But actually, the topic of differential equations is an entire course in college. So there's a lot to this. So this is a very simple differential equation. It's the derivative of some function y with respect to x is 3x. Um, we are looking for the function where this is true. Well, um, basically, if dy dx equals 3x, then y would be equal to the integral of 3x dx. Basically, it's like, hey, I took the derivative of something, I got 3x. So what is that thing? Well, why don't I integrate 3x to find out what that was? All right, so that would be 3 halves x squared plus c when I integrate. So because constants, when you take their derivative, they go to 0, there can be multiple solutions to a differential equation. So is there just one solution? No. So one solution, the general solution, is y equals 3 halves x squared plus c. That's called the general solution. But there are many specific solutions, like 3 halves x squared plus 2, or y equals 3 halves x squared minus 17, etc. You could plug in any real number. Now, if I know a single point on the function y, then could I find the particular solution? Well, if I know that 1, 4 is a solution, as a point on this graph, I could plug in 1, 4. So I would have 4 equals 3 halves times 1 squared plus c. And I think you can see that there's only going to be one solution to that equation. So it'd be 4 minus 3 halves equals c. 4 is 8 halves minus 3 halves. C would be 5 halves. So this particular solution, y equals 3 halves x squared plus 5 halves. All right, so this point is called an initial condition. Okay, so just to recap, when you have a differential equation, the general solution will have a plus c. There'll be multiple answers. But if you're given just one point on that graph, you can figure out the value of c, and then we can find the particular solution. So this was a particular solution with that initial condition. Okay, so those are some words that you should, initial condition, particular solution. Those are some words that hopefully you'll keep in mind. So solve the following differential equations. So here you're given that the derivative is root x, f of 4 equals 6. What's that called again? Initial condition. All right, so I will integrate root x dx in order to find my function f of x. That is the same as x to the 1/2. Add 1 to the exponent, multiply by the reciprocal, plus c. So that is the general solution. In order to find the particular solution, I plug in the 0.46. So 6 equals 2/3 times 4 to the 3 halves plus c. The square root of 4 is 2. 2 cubed is 8. So 6 equals 16/3 plus c. 6 is 18/3 minus 16/3 equals c. So c equals 2/3. So my particular solution is f of x equals 2/3 x to the 3/2 plus 2/3. All right, so that's my final answer on that one. This next example, if you notice, we're starting off with the second derivative. So I'm going to have to integrate twice because when I integrate 2x, I'll get the first derivative. So notice I've been given a point on the first derivative and a point on the function itself. So f prime of x will be equal to the integral of 2x dx, which if I integrate is x squared plus c. All right, and I'm going to use this point. So plug in -1, 2. So I have 2 equals -1 squared plus c. So that means c equals 1. So that means the first derivative is x squared plus 1. Okay, but I'm looking for the function, so I got to go one more. So f of x is the integral of x squared plus 1 dx. So it's 1/3 x cubed plus x plus c. Different c than the above c. All right, I know a point on the function f of x is 3, 1. So 1 equals 1/3 times 3 cubed plus 3 plus c. So that'd be 9 plus 3 is 12. So it looks like c is -11. Excuse me, folks. So my final answer is 1/3 x cubed plus x minus 11. All right, that's what we needed to cover in this lesson, folks. Hope that's making sense. Let me know if you have questions. I'm really sorry that I'm not there with you guys. Hopefully this COVID thing's going to go away soon and I can come back. All right. Let me know if you have questions. Bye.